Okay, all right. Thank you. So thank you for coming. So I gave a tentative title for the talk, which is called Pushing the Boundaries of AI, and it's sort of suitably vague. So maybe I shouldn't do that now. And really, this is what I want to talk about. So models beyond your typical deep nets. Right? So hopefully the past few days you've heard about, at least from the CVSSP, how we use deep neural networks to solve computer vision tasks, right? And these tend to be your typical convolutional neural networks. So this is by far one of the most popular applications. If I can get the screen back. Let me see. Why is that going? Okay. Let's see if that happens again. Okay. So this is a success stories of deep neural networks in computer vision. So about 10 years ago now, the ImageNet data set came out, and it's quite a large data set containing about 1 million images, where there is about 1,000 different categories of objects, of which we would like to train a computer using computer vision techniques to automatically categorize, right? So you've got cars, mushrooms, cherries, and things like this. And so one of the ways, so people have been trying to do this for a long time, and eventually convolutional neural networks came about, which is, hopefully you've heard about it yesterday. So it takes in some kind of input images and applies convolutional filters in a sequential manner. So each filter is essentially trying to look for specific types of features in the image, and the whole point of this deep learning is that given this kind of architecture of filter after filter after filter of trying to find relevant images, is like, how do you actually find those filters? Okay, so the first one is one of the ones which made it successful was AlexNet, and it's you've got your input image, and then you have convolutional filters which scans the image for low-level features, then gives a response map, of which then you apply more and more filters to build up higher and higher level information. And of course, once they found that worked, then it sort of opened the floodgates to this type of models for basically classifying images. So you give an image, and then it tells you what's the probability of certain categories occurring inside the image. Now, so AlexNet is one of them. VGGNet is the one which followed, and it gets ever and more complicated, right? Deeper and bigger. Okay, so if you hear about deep nets, AI, and things like that, and computers being able to find or recognize objects inside images, it tends to be this is what they're talking about. Okay, so but the purpose of my talk is to tell you that you don't have to, it's not all restricted to this kind of architecture, right? There are other things which you can do, the weird and wonderful world of deep nets. It's not just, there's a whole zoo out there. Okay, and you've seen others as well in terms of recurrent networks for time series and things, but there's even more slightly exotic networks. And so the point which I'm trying to bring across here is that they all work with a number of assumptions, and we'll see what that is. And if you can satisfy those assumptions in your model, the model which you build, you can then perform deep learning. It doesn't have to look like a neural network or a convolutional network. Okay, so here's an example of maybe a network you might or might not have seen before. It's called a wavelet neural network. Okay, so it's quite different to your normal network where you have got a neuron, takes in all the inputs, sums it across, and then passes it to an activation function or a convolutional filter. So the neuron is slightly different in that it's trying to look for a wavelet, a type of wave inside your signal, and that's not necessarily applied to computer vision. One of the interesting applications is you give it a noisy signal and it denoises it for you. Okay, and you can see that it's better than your typical filtering method. Okay, so then another thing which we work quite a lot with here is using deep nets, but not deep nets on their own, to perform not classification. So classification is the straightforward application of neural networks or sort of deep learning style models. Give it an image, tell me what category that image is. Now, we have another challenging area as well, which is to do with retrieval. Now, retrieval is different in the sense that classification, you have fixed, let's say, 1,000 different categories in which you want your computer to automatically recognize, right? But in terms of retrieval, there is no number of categories. There will be a task of, I've got different landmarks inside the world of which I've taken a picture of, and I've got a big data set of these photographs here. I've given a new photo of which is somewhere in some landmark there. We have to then quickly search through this data set. So where does deep neural networks come in here? You know, there's no classification. I'm not recognizing landmarks because there are hundreds or thousands of landmarks everywhere. Nobody's going to label them properly, right? So, but what we can do is we can use deep neural networks to provide what we call as deep features of compact, efficient representation, which captures the content, the important semantic content of an image. So, for example, you know, I've taken a picture of on my phone of this place at night, and my data set contains exactly the same place, but in the daytime. Now, visually, it looks completely different, right? We know that it's the same because we have high-level semantic understanding of like this. We know what to look for, and despite the fact that it's been taken at different angles, so there is that booth there which is different. So how do we do that, right? So we still use a deep net, but it's a deep net which is slightly different to how you see it. So we have your existing convolutional neural networks, and then on top of that we put in another so-called aggregation layer. Okay, but we can learn it all together using deep learning. But again, you know, this doesn't look like your typical deep net where you've just got neuron after neuron after neuron, right? And then finally an output. There is something else going on inside there. But nonetheless, people have found ways of incorporating this aggregation of neural network middle features in such a way that it can give us a representation of those images which we can then use to very, very quickly find relevant examples in our data set. Okay, so for me to do that, so there's three things I'm going to talk about. One which is how can we make that possible, right? So how can we go away from your typical neural network architecture and still deploy all of the deep learning methods which we have found to be useful so far, okay? So at the heart of deep learning, hopefully you would have known by now, is backpropagation, right? Worryingly or not, the current use of backpropagation is basically the same as the one which was found in the 80s, right? With all its problems. So we solved the problems which it faces, but not necessarily, the fundamental technique for learning hasn't really changed that much, okay? So the way, why can we use backpropagation? So if you know calculus, backpropagation is just a chain rule, right? So the entire mathematics of deep learning is powered by a simple chain rule. So what is that? So we can start thinking about neural networks not as this kind of thing, but really a composition of functions. Okay, so let me tell you be a bit more specific like this. Okay, so you've got your input layer, you've got your hidden layer, you've got your output layer. But really, you know, what's going on here is that your hidden layer is doing something to the inputs, right? So you've got, let's say you've got two inputs, X and Y, each of them giving some values there. Your hidden layer will add those values and multiply them with some numbers together, and then output three values, okay? So you can think of that as just a function, and the same for the output layer as well. Okay, so what does it mean for learning? Well, if you've got A and B and that's governed by your training data, you can't change that. The input is going to be what the input is. But the whole point of this deep learning is that we were given inputs of some types, you know, like let's say positions of images, and we have been given outputs as well, labels, yes or no. Right? This input corresponds to a yes, that input corresponds to a no. And the whole point about deep learning is this game where we have levers which we can tweak, which are these weights here. So yesterday you would have seen that a deep neural network, or at least a neural network, is simply, weighted combinations of the inputs, yeah, and then you output it via some other function there. Okay. So instead of thinking about that like this, we can just think of it like this. We have some kind of input, we have a function, of which in this case here we have 6 levers where we can tweak the numbers of, and another function which we then, which takes in the inputs of the previous layers, of which it has various levers where we can, or parameters where we can tune as well. Okay, and really the deep net is just this function processing the output of this function, which processes the output of those functions there. So mathematically, it's just a function composition, right? G f of x. So, and of course, for the purpose of learning deep nets, well, we need 2 things, right? We need 3 things. We need a model to transform some input into some output. So we need a label data set to tell you what's going on. So we have an input, let's say X, a label data set, which you already know. So examples and their corresponding labels. And of course, you need to know or somehow be able to judge whether the deep net is doing well or not. Okay, so so you need a cost function. Like in this case here, it's just how different is the output of the deep neural network to its label, right? And you sum it across all of the outputs of the input, given the inputs. Okay, so in terms of this, so the whole point of everything is that what we want to do is, given that cost function will give us different values depending on how we adjust the deep net parameters, right? So we want to adjust it in such a way that, let's say C is the cost, up is bad, and the lower the cost is, the better our deep net is doing, right? It's fulfilling its task of transforming input data into the right output data, whatever that is, okay? And so we can go off and search all possible values, and we see there's this landscape of cost. And as we adjust the neural network's parameters, let's say the first weight, the second weight of its neurons, we get better and better, potentially, neural network configurations, right? Or which is where you see that. And really what we want is this mechanical way, which we can code into a computer, of telling us, okay, I am here now, I've got my neural network is configured in this way with these weights here, and it is so good or so bad at doing what it's meant to do. Now, how do I then tweak the parameters in such a way that I improve the best I can, right? And that translates to, inside this little landscape of doing good or doing bad, going down into a valley where there is a little minimum. So ultimately, what that's done is that we want to tweak the cost function over there, C, with respect to, we want to know how the costs change if we were to tweak like V1, W1 in this case here, okay? And but the parameters of this deep nets is hidden deep inside this C function. So C is a function of our neural network and our input data. The input data is constant, that doesn't change. What we can change is the configuration of the deep nets there. So that's really what we want. We want some kind of way of extracting an equation, a specific mathematical equation, which tells us, okay, if you tweak it in this way, it's going to go so much in this way there. And it turns out that, so this is the all of back propagation, right? You can achieve that by using the chain rule. So if you know calculus, C is a function of f, which G, which is a function of f, you can decompose that into these 3 gradients there. That just tells you that how does the cost change when your neural network's output changes, right? Okay, but how does your neural network's output change? Well, that depends on, how does the output of this neural network change? Well, that depends on how you change the layers previously there, because it's all chained together, right? Sequentially. So if you change weights, which is in F, in the hidden layer, that affects what happens in the output layer as well. Okay, so that needs to be accounted for, and that's the last one there. So what it is this? It is basically this. This is deep learning at its heart, right? Now you can do clever things on top of this, but at its heart of it, it is this being able to know how to change the cost function for the best in such a way that the neural network performs better in the most optimal way. It is just, you just multiply these three things together. Okay? So now G is one of the, like, if you use neurons, then it's just a weighted linear combination. It's the same for F as well. But, so I'll just make one point here. Why am I telling you all this, right? I'm telling you this because if you can express your neural network in a mathematical function, f, like f equals to sine x, that kind of thing, y equals to sine x, that's a mathematical function, right? So if you can express each of the layers in terms of those kind of analytical functions, you can do deep learning on that. So it doesn't have to be this specific neural network architecture, which is this neuron taking 5 inputs, thresholding it, or passing it through sigmoid there. Okay, so that's the point. So if you can write out and calculate those equations in the chain rule there, then you can move away from this, which is your standard deep net, which is you have some inputs, and then those inputs will get multiplied with some weights. So different inputs have different importances. You sum them all up together, and you pass it to some kind of function, which will transform it into maybe a value between 0 and 1. Okay, so you don't have to do that. Well, you can. Well, you can do other things as well, right? You can do things like, okay, what if my neuron is not the shape of a sigmoid, right? What if my neuron's output was the shape of a wavelet? Like a wavelet is a little wave which doesn't go on forever, right? So it sort of decays as you tend to both infinity and negative infinity. So these are two popular wavelets here. There's lots and lots of nice properties of that, but they decompose signals into their constituent parts, right? So here's an interesting neural network which is not often seen. So you can have, here's a neuron. So what's a neuron, right? So a neuron is just, it takes in an input, U, right, and it tries to do something with it, just like my multiple input neuron. There are things I can tweak about it now. So in the, if we see what's different to this, in the traditional deep net here, what can you tweak inside this neuron here? You can tweak its weights, right? So how to linearly change the inputs. But then once that's done, you can pass it to this function, the activation function. That's fixed, right? You've chosen it, and there's nothing you can do about it. Okay. So, but in this kind of architecture, you can do both. You can change your input. You can make it a bit stronger, a bit weaker, and you can change the shape of the outputs as well. So essentially, each neuron here no longer represents like this increasing or thresholded firing. It represents a little wavelet, yeah? And depending on how you configure it, right, how you adjust, it's got like 2 levers inside this, this neuron here, which determines the shape of this wavelet here, and we can learn that as well, okay? So that's one neuron. Of course, then because it's a neural network, you can combine them together into a bigger network. So you can combine multiple of these waves together in such a way that when you give it some input, it will add, you know, the responses of these ones here together. And so how is this used? So essentially what this neural network now does is that it is representing a number of different waves, yeah, which are then added together, which will give you another wave, right, which is hopefully the thing which you're looking for. You're learning it. Okay. So this is different, right? So can we do that? Yes, because, you know, if you recall, the neuron, which I used to call f as a function, right, is all we need to do is to be able to differentiate that function, which means that what does it mean to differentiate it? To find a slope in that function, right? So if we restrict ourselves to analytical functions, the typical stuff which we all love and know, x squared, exponentials, then we are guaranteed to be able to do that. So yes, this is differential. We can use this in the deep learning framework. Doesn't have to conform to your normal standards there. We can write out, don't worry about the details of that. The reason why I put this here is that to show that we can write out a mathematical equation. It looks complicated, but it's sort of tractable in that there's lots of symbols inside there, but what is inside there is sort of, there's no infinities inside there, right? So there's no sums of infinity. It's just a normal looking equation, albeit slightly complicated, but we can write it out down. So that's a cost function, tells us how bad or good our neural network is doing. Yeah. The neuron itself, that little wavelet, has a few parameters, right? We can make the input signal stronger or weaker, like the weighting of the thing. It's got this, the wave can be stretched or compressed, right? So these are all the different parameters which we can tweak, right? And because that neuron is a normal function, so analytical function, we can compute these partial derivatives or the gradients, right? How do you tweak the parameters in such a way that it would improve the neural network as best as it can, right, in an incremental way? Okay, so what's the use of all of this? So one of the examples of its use is denoising. So we've got a really noisy signal like EEG, or in this case, let's say a toy example, sine wave, right? We don't really know, it looks like a sine wave, we can sort of see it, but we don't really know. It's lots of jagged going ups and downs. We can sample some number of examples which are noisy, but inside there is a clean signal. We would like to recover that clean signal using this wavelet combinations. So what we can do is we can learn this kind of architecture which says, how do you configure these little different waves together in such a way that it would fit as best as it can into the signal there. And what they found that you can do this kind of thing. So if you learn a wavelet network to represent those little noisy dots over there, you come up with something which produces this curve here. So it is this wave added by that wave added by a little bit of that wave equals that. So the green is the real signal and the blue is the not real signal. Okay, right. Okay, so that's toy. So somebody actually tried to make some use of this. And one of the applications of this is in Singapore. So they have forecasting solar irradiance, sunlight. How much sunlight is there going to be? Okay, so they've got multiple locations where they measure how much sunlight they have. They have a neural network which is based on that kind of wave. Combine them together, and they can make predictions. We give it 5 hours of data in the past. Tell me what's going to happen after using the wave. And this is what they found, right? It fits quite well, so it's certainly useful. So this is an hourly prediction, a 15-minute prediction, and an hourly prediction over there, right? So they give it like 4 hours before or 10 hours before, and then tell me what's going to happen next. And so the actual is the green one, and the black one is the predicted one. Okay, so that's a slightly different type of neural network, right, that we tend not to see. Okay, right. Okay, so now coming back to running out of time, but I'll bring it back to computer vision because I do lots of vision, and we work quite a lot in retrieval. So what is retrieval? It's basically, like I said, we have a database of lots of photos at different locations. I give a photo, Google image search basically. I give a photo of some taken at some location, and the computer needs to search through very, very quickly all of these images in such a way that it gives me back, hopefully, a photo at at that location there, right? So now it's not as simple of just comparing stuff, because you can't just compare image with image. How can you compare that nighttime image with that daytime image taken at a completely different viewpoint, right? So it looks completely different visually. So we need to do some kind of processing to that image itself in order to make searching possible. Okay, there are a couple of other challenges which we have to account for as well. Data sets are large nowadays. So they are not just tens, hundreds of images, there are millions and millions of images now. So again, you know, even if we have a good representation for the content of an image, if we still at some point have to do a one-to-one comparison. Now if that description of the image content is very, very complex, then this is going to take a long time and it's not going to be a useful method. Okay? So, and the other one you've seen is that when people take pictures, they don't take it at exactly the same place and exactly the same angle, right? So all kinds of visual variations will be present. So what's the solution? The solution is to make an efficient and compact representation for the content of the image. So this is not a class, this is not a category, this is just somehow we need to find mathematical, a feature vector whose values inside there is uniquely captures the semantic, the location of that image, okay? And it has to be robust to all of the, different viewpoints of taking the picture, zooming, lighting conditions. So how do they do that? It's a combination of deep nets, of course, and aggregation methods, but tied together such that they're not separate stuff. They're tied together such that they are learned and tuned at the same time. Okay, 5 minutes. Yeah, how much? 1 minute. Okay, that'll be that. All right. Okay, so let me give you the gist of what we do. So DNNs, we know that they extract different amounts, different types of information. So you've got low-level information at the start of the DNN, extracting corners and things like this. Automatically, it learns it for itself. Then it assembles this information into middle-level features, and it gets increasingly more and more high-level, right? So at this layer there, it's starting to look for essentially objects or important things which have high-level semantic meaning. And that's what we leverage on. So what's the process? We give it to some typical deep net, an image, extracts out some kind of high-level features which represents, it's like an arch, a corner of a black building and things like this, and we aggregate all of these features together in this manner here. So the representation is not very important, but we have, we found, let's say, 49 different visual features for it. We need to just crunch it down to just one feature, one representation here. Okay, now, but it turns out that, so in the past it was two different operations. We learn the deep net on its own, then we go and do this completely on its own as well, right? So there are representations of like important descriptors for that. But what people have found is that you can mathematically write out, again, the equations for doing that aggregation together. And because you can do that, you can put that into a deep net, like the way I've suggested just now. It's just a composition of functions, which you can, if you can express them mathematically, then you can use that to basically do that and perform image search. And this is the results. It's quite amazing, right? So it manages to find sort of similar landmarks, despite the fact that once at night, once in the day, half the things are not visible sometimes. So, okay, so that's my summary, which is, so we've seen like, two different types of neural networks, which are different to your typical deep nets. But the reason why you can do that is because, back propagation doesn't really care whether you are a neural network or anything, it just cares that you are a nicely well-behaved function composition. Okay, now, of course, then the open question is, will they be better, just because you can doesn't mean you should. Okay? Right. Okay.
Thanks very much.
Thanks.